Okay, class, we are now starting on a somewhat interesting but yet challenging area in A&P1. I would say that this is just as challenging as the chemistry chapter, which I'm sure most of you feel the same way, as far as chemistry being somewhat difficult. This particular topic is going to be electrophysiology. Now, this is an excerpt from the chapter in nerve tissue. This is an excerpt, so it's not a full chapter, but I'm making it a module. I'm making it a module because I think it is worth that to be dedicated to, a module. Okay. Now, in my website, I have an electrophysiology, what I call general electrophysiology PowerPoint file. And then I have an electrophysiology of muscle file. So I actually have two. But I'm adding a Microsoft Word document that I made very recently called Electrophysiology, a simple version. So this will be an MS Word document that I'll have. Now, the general electrophysiology I have and the electrophysiology of muscle are very detailed. They're very good, but they may be a little challenging. So I wrote this, since we're not doing face-to-face, to kind of help you. And then you can glance at those two. So this is kind of my suggestion on how to study electrophys. Print out this document here and read it several times. Look at the videos I'm going to make about this document and look at them two or three times. In the text, the one we're using, pages 398 to 422 discuss electrophysiology. Now, some of you have different versions of the test, older versions. Some have others. So you're looking for electrophysiology in your particular text. But in the one we're using, it should be 398 to 422. I will have two or three, I'm assuming, motion videos, and you'll see on this, because some of this involves kind of what you'd like to see in more of a motion. And then, of course, don't hesitate to ask your tutors questions or ask me questions. So this is kind of what I'm looking at as far as how you should approach electrophysiology, okay? All right, so let's get started. And like I said, there'll be a few videos on this, and we'll see where this goes, okay? Electrophysiology, a simple version, is all about the gates, the ion channels. The whole thing of this has to do with ion channels. Channels that bring ions in and out of the cells. So all these different gates create different potentials in the cell membrane. And so that's why I call this all really about the gates. All right. So let's get started here and see what we got. Every living cell has a charge on its membrane termed a resting membrane potential. So every cell has that. The resting membrane potential is due to cell membranes having what we call passive leak channels, or some books call them gates. Passive leak channels. A passive leak channel is a transmembrane. That means it goes all the way through the membrane, just like you see that. Integral protein, remember integral proteins are within the membrane, but this one goes all the way through as integral protein that is generally always open, allowing passive transport movement of certain ions into and out of the cell. Okay. The main ions of interest involved in the resting membrane potential are sodium, potassium, chloride, and something we'll call the large molecular anions. These are big proteins made inside the cell and are too big to get out. These are big proteins made inside the cell and they're too big to get out. That's what and they have a negative charge, large molecular anions. Okay? I'm going to say that the resting membrane potential has a static position. Now, what I mean is it kind of sits in one place. That's not completely true, but it does differentiate it from what I'm going to talk about in a moment. So I'm going to say that it kind of sits in one place. Let's say no lateral movement on the cell membrane. And it does have some, but I'm using this to kind of help you differentiate from what I'm going to do in a second right now. Okay? Certain cells, though, nerve and muscle, can laterally move the charge along the membrane. I mean, truly laterally. Propel it, we can say. This is termed conductivity. Okay? Conductivity is just like you would do with electricity moving along a wire. Conductivity. That's what conductivity would be. Okay? This conductivity is due to nerve and muscle cells being able to create action potentials. See, this is a resting membrane potential, but they can create action potentials. Why can the nerve and muscle cells create action potentials? They have voltage-dependent gates. See, they have some additional gates in addition to the passive leak channels. They have additional gates in addition to those. Let's go further. Okay. How do voltage-dependent gates differ from passive leak channels? Okay, here we go with this now. Voltage-dependent gates are generally always closed. See, these were always open. And only open when the proper voltage is applied to the membrane. That's why they call them voltage dependent. Only nerve and muscle have these. Because they have these, they can create action potentials which can cause conductivity. So you got to get your points together. Okay? Voltage dependent gates, like passive leak channels, are transmembrane integral proteins that allow the same ions in and out we just discussed, which would primarily be sodium and potassium. Sodium and potassium. But they are generally closed and only open when necessary. And that has to do when a voltage is applied. The voltage necessary to open it, see, there's a certain voltage you have to reach. There's a certain voltage you have to reach to do it, and that particular voltage is called threshold voltage. Threshold voltage is the voltage necessary to open the voltage-dependent gates, which can then create action potentials, which can then initiate conductivity along the nerve and the muscle. Hopefully you kind of see where I'm going with this now. Are there other gates involved in electrophysiology? Yes, there are. And these are called ligand-dependent gates, ligand-gated channels. And then we have some that open into, like, for mechanical factors, like if you put pressure on something, like pressure. Some open and close in response to light. That would be like the retina in your eye. The retina, which is at the back of your eye, responds to light, and it opens channels and so forth. So there are different channels. That's why when I started out, I want to tell you, it's all about the gates. It's all about the gates. Okay? What is a ligand? Remember we said ligand-gated channels. It's a generic term for any substance that can attach to a receptor. So that means this substance attaches to the receptor and opens up the ligand-gated channels. Okay? Hopefully this document can help you. Some ligands are chemicals known as neurotransmitter substances. And that's what we're going to really focus on much later in these videos and in this particular document here. Some are hormones also, and some are other chemicals. But we're going to focus on neurotransmitter substances in this document, which also would have been focused on in the text when you read those pages. Okay? Just as with voltage-dependent gates, the ligand-gated channels are generally closed and open only when the proper chemical binds to the receptor. See, again, passive leak channels were the only ones that stayed open all the time. These others are generally closed and open only when something comes along. Okay? The ligand-gated channels also are transmembrane integral proteins that allow ions in and out. So the difference is what makes them open. In one case, it's ligand for ligand-dependent gate, and then for the others, it would be voltage dependent, voltage to make it open, threshold voltage. For the resting membrane potential, nothing, because the gates are always what? Open. Okay. Now, what kind of potentials do the ligand-gated channels give? Remember, we had passive leak channels, we had voltage-dependent channels, so we had resting membrane potential for the just open gates, action potential for the voltage-dependent gates. What do you call the ligand-gated channels? What kind of potential do they do? If it's a nerve cell, they give an EPSP, excitatory postsynaptic potential, or an inhibitory postsynaptic potential. We'll talk about that later. If it's a muscle cell, they give what we call a motor end plate potential. Motor end plate potential. We'll talk about that later. Okay? So this is where we've gotten to now. All right. So our first discussion is going to be on the resting membrane potential. So I like to make these videos where you know where you are. So I'm going to end this video, which I'm going to call more of a general discussion, and then start on the resting membrane potential. Okay?